July 3, 1938. Stoke Bank, Lincolnshire. The streamlined locomotive that German engineers swore would destroy itself was about to attempt what every physics calculation said was impossible. Sir Nigel Gresley's Eleanor Class A4 Mallard sat idling at Grantham Station, its wedge-shaped nose gleaming in the morning sun. For 18 months, this machine had been the subject of ridicule from established railway engineers who understood one fundamental truth: steam locomotives had physical limits that no amount of clever design could overcome. Continental engineers had calculated those limits precisely. 120 miles per hour represented the absolute ceiling where boiler pressure, wheel balance, and track harmonics converged into catastrophic failure. Beyond that threshold, the rotational forces would tear drive wheels from their axles, boiler tubes would rupture from steam demand, and track oscillations would derail even the most carefully balanced machine. Professor Hermann Kemper's published paper from the Deutsche Reichsbahn had been explicit. English attempts to exceed established velocity parameters through cosmetic streamlining demonstrate a fundamental misunderstanding of thermodynamic principles. His calculations showed that steam generation rates could never match the power demands of sustained high-speed operation. The Great Western Railway's chief mechanical engineer, Charles Collett, was equally dismissive. His Castle-class locomotives represented proven British engineering, powerful, reliable machines that operated efficiently at speeds railway companies actually needed. Gresley's streamlined experiments are showmanship masquerading as engineering, Collett told the Railway Gazette. Passenger service requires dependability, not record attempts that serve no practical purpose. But Gresley had been studying something his critics overlooked. Aerodynamic resistance increased exponentially with speed, and conventional locomotive designs fought that resistance with brute force rather than efficiency. His calculations suggested that reducing air resistance could fundamentally change the power-to-speed equation in ways that traditional engineering hadn't considered. The streamlined casing that covered Mallard's running gear wasn't decoration. It was an integral component that channeled airflow around the locomotive's irregular surfaces. Where conventional engines pushed a wall of turbulent air ahead of them, Gresley's design sliced through atmospheric resistance like a blade. Critics called it unnecessary complexity. The streamlined panels added weight, complicated maintenance access, and required specialized fabrication techniques that conventional locomotive construction had never demanded. Sir William Stayner, chief mechanical engineer of the London, Midland and Scottish Railway, summarized the prevailing opinion: the weight penalty of streamlining cancels any theoretical aerodynamic advantage. We're building locomotives, not aircraft. Yet Mallard had been quietly proving otherwise during regular service runs. Driver Joseph Duddington reported something unusual. The locomotive felt more stable at 100 miles per hour than conventional engines did at 80. The streamlined casing wasn't just reducing drag, it was managing airflow in ways that improved high-speed handling characteristics. As test preparations began that July morning, Gresley faced professional extinction if the record attempt failed. 3 years of development, £8,000 in specialized construction costs, and his reputation as Britain's leading locomotive engineer all rode on whether steam technology could exceed limits that established science said were absolute. The German railway establishment had thrown down a gauntlet that British engineers couldn't ignore. On May 11, 1936, Germany's streamlined 05002 locomotive achieved 124.5 miles per hour during a test run near Hamburg, establishing what Deutsche Reichsbahn proclaimed as definitive proof of German engineering superiority. The achievement stunned British railway circles. Germany had not only built a faster locomotive, they had demonstrated that sustained high-speed operation was achievable with proper engineering. The 05002's performance validated streamlining principles while simultaneously suggesting that British steam technology had fallen behind continental innovation. Gresley analyzed the German success with methodical attention. The 05002 utilized a 3-cylinder design with sophisticated valve timing that maximized steam efficiency at high rotational speeds. Its streamlined casing was more comprehensive than anything British manufacturers had attempted, enclosing nearly the entire locomotive in a smooth aerodynamic shell. But the German achievement came with limitations that Gresley's engineering instincts recognized. The 05002's record run had been conducted under ideal conditions: perfectly maintained track, minimal train weight, and a carefully selected route with favorable gradients. The locomotive's practical service record showed frequent mechanical issues that suggested its high-speed capabilities came at the cost of everyday reliability. British railway companies faced a different operational reality. The London and North Eastern Railway operated intensive passenger schedules across varied terrain that demanded locomotives capable of sustained performance rather than occasional record attempts. Gressley needed to design a machine that could break speed records while maintaining the reliability that commercial service required. The streamlining debate intensified as Gressley developed his A4 class design. Traditional British locomotive engineering emphasized accessibility, every component easily reached for maintenance and repair. Streamlined casings complicated that philosophy by concealing running gear behind panels that required removal for inspection. The railway workshops at Doncaster resisted Gressley's specifications. Master craftsmen who had built locomotives for decades questioned why proven designs needed modification to chase speed records that served no practical purpose. The additional fabrication work required for streamlined panels disrupted established production schedules and demanded skills that traditional locomotive construction had never needed. Financial pressure mounted as development costs exceeded initial projections. The Laner's board of directors questioned whether Gressley's experimental locomotives justified their expense when conventional designs met operational requirements at lower cost. Each A4 locomotive cost approximately £8,000, nearly 15% more than equivalent conventional machines. Gressley's defense focused on operational efficiency rather than speed records. His calculations showed that aerodynamic improvements reduced coal consumption at sustained high speeds by nearly 20%. For a railway company operating dozens of express services daily, that efficiency translated into substantial fuel savings that could justify the higher initial investment. The first A4 locomotives entered service in September 1935, their distinctive streamlined appearance immediately recognizable across Britain's railway network. Initial performance reports validated Gressley's efficiency claims. The streamlined engines consumed less coal while maintaining schedule speeds that conventional locomotives achieved only through higher power output. But the real test remained unattempted. Could British steam technology exceed the German record and prove that streamlining represented genuine engineering advancement rather than cosmetic modification? The Mallard's construction represented 3 years of systematic innovation in areas that conventional locomotive design had considered settled engineering. Gressley's team at Doncaster Works approached each component as an opportunity to exceed limitations that tradition had accepted as immutable. The boiler system incorporated modifications that increased steam generation capacity by 12% compared to standard A4 locomotives. Gressley specified a higher heating surface area through additional small tubes that improved heat transfer efficiency without increasing overall boiler dimensions. The firebox received a combustion arch that created more complete fuel burning, extracting maximum energy from each shovelful of coal. Inspector Sam Jenkins supervised the boiler installation with particular attention to tube expansion joints, the connection points where countless locomotives had failed through metal fatigue. Each tube received individual stress testing at pressures exceeding operational requirements by 40%. The inspection process took twice as long as standard practice demanded, but Jenkins understood that boiler failure at record speeds would be catastrophic. The valve gear that controlled steam distribution to the cylinders incorporated Gressley's conjugated system, a mechanical arrangement that operated the middle cylinder's valves through a linkage connecting the outside cylinders. This eliminated one set of valve gear, reducing weight and mechanical complexity while maintaining precise steam timing across all 3 cylinders. Critics had questioned the conjugated system's reliability, arguing that mechanical linkages introduced additional failure points. But Gressley's calculations showed the weight savings improved the locomotive's power-to-weight ratio significantly, a critical advantage for sustained high-speed operation where every pound of excess mass required additional power to accelerate and maintain. The wheel balancing process extended beyond conventional practice into precision engineering that locomotive workshops rarely attempted. Each driving wheel received individual dynamic balancing that measured rotational forces at speeds up to 130 miles per hour. Specialized equipment detected vibration patterns that would become destructive at extreme velocities, allowing technicians to add counterweights in precise locations that canceled unwanted oscillations. The streamlined casing itself represented fabrication challenges that traditional locomotive construction had never encountered. Steel panels curved in 3 dimensions required forming techniques borrowed from shipbuilding and aircraft manufacturing. Each panel was fitted to within 1/8 inch tolerance, creating smooth contours that channeled airflow without the turbulence that gaps and irregularities would generate. The keel-chap double-chimney exhaust system represented perhaps Gressley's most significant innovation. French engineer André Chapillon had developed this design to improve draft efficiency, the process by which exhaust steam creates suction that draws air through the fire and improves combustion. The system used two separate exhaust passages that created more effective draft while reducing back pressure that conventional single chimneys imposed on the cylinders. Installation of the keelchap system required extensive modifications to the locomotive's smokebox, the chamber where exhaust steam exits after passing through the cylinders. The double chimney arrangement demanded precise alignment to create the Venturi effect that made the system effective. Misalignment of even a few degrees would eliminate the performance advantages while adding weight and complexity. By June 1938, the Mallard had completed 6 months of regular service, accumulating operational data that validated its specialized systems. The locomotive consistently outperformed sister engines in coal efficiency and sustained speed capability. Gressley's engineering team believed they had created a machine capable of exceeding the German record, if physics and track conditions cooperated. Planning a record attempt required coordination that extended beyond simple locomotive preparation. The London and North Eastern Railway needed to secure a route section where track condition, gradient profile and operational clearance converged to create ideal conditions for sustained high-speed running. Stoke Bank between Grantham and Peterborough offered the necessary characteristics. The 4-mile descent provided a consistent 1 in 200 gradient that would assist acceleration while remaining gentle enough to maintain control. Track maintenance crews had recently completed renewal work that ensured rail alignment met the precise tolerances that high-speed operation demanded. The Railway Inspectorate required comprehensive safety protocols before authorizing the attempt. Inspector Colonel A.H.L. Mount reviewed every aspect of the planned run, from locomotive mechanical condition to emergency procedures if something went catastrophically wrong. His approval came with stipulations. The test would occur on a Sunday when regular traffic was minimal, and emergency response teams would be positioned along the route. Driver Joseph Duddington received the assignment based on his unmatched experience with high-speed locomotive operation. At 61 years old, Duddington had been driving express trains for over 30 years, his hands reading subtle feedback through throttle and brake controls that younger drivers hadn't yet learned to interpret. He understood how locomotives behaved at the edge of their performance envelope, when to push harder and when mechanical stress patterns warned of approaching limits. Fireman Thomas Bray would manage the boiler throughout the attempt, maintaining steam pressure at maximum safe levels while monitoring water levels, fire condition, and the dozens of gauges that provided information about the locomotive's internal state. Bray's skill would directly determine whether the Mallard could sustain the power output that record speeds demanded. The test train consisted of the Mallard and 6 coaches, the dynamometer car containing recording instruments, followed by 5 standard passenger carriages ballasted to simulate a typical express train load. Total weight came to 240 tons, heavy enough to provide meaningful performance data while light enough to allow maximum speed potential. Inspector Jenkins conducted final mechanical inspections on July 2, examining every component that would face extreme stress during the attempt. Driving wheel journals received particular attention. The bearing surfaces where wheels connected to axles and any imperfection in lubrication or alignment would cause rapid heating that could seize bearings at high speed. The weather forecast for July 3 showed favorable conditions, clear skies, moderate temperatures and light winds. Atmospheric density affected locomotive performance measurably, and cool morning air provided denser oxygen that improved combustion efficiency. Gressley addressed the crew at Grantham Station on the morning of the attempt, his instructions characteristically direct. "Gentlemen, we're attempting to demonstrate that British steam engineering can exceed any speed record currently held. Drive the locomotive as you would any express service, safely and professionally. The machinery will do what we designed it to do." As the Mallard departed Grantham at 4:30 p.m., accelerating southward towards Stoke Bank, decades of engineering theory were about to face practical validation. The streamlined locomotive that critics had dismissed as unnecessary complexity was about to either vindicate Gressley's vision or prove that physics had limits that clever design couldn't overcome. The acceleration down Stoke Bank began normally, Duddington opening the regulator gradually as the gradient assisted the locomotive's gathering momentum. At 70 miles per hour, the Mallard's behavior matched expectations, its 3 cylinders driving the wheels in the smooth rhythm that characterized well-balanced steam locomotives. At 90 miles per hour, the aerodynamic advantages became evident. Where conventional locomotives fought increasing air resistance that made each additional mile per hour harder to achieve, the Mallard's streamlined casing was managing airflow with visible efficiency. The characteristic roar that surrounded high-speed steam locomotives was noticeably quieter. Less turbulence meant less energy wasted pushing air aside. Inspector Jenkins, positioned in the dynamometer car, watched recording instruments capture data that would either validate or refute 3 years of engineering theory. Speed indicators climbed past 100 miles per hour as the locomotive entered conditions where conventional designs encountered the mechanical limits that engineers had long considered absolute. At 110 miles per hour, Duddington felt something experienced drivers recognized: the transition point where a locomotive's handling characteristics changed fundamentally. Conventional engines became unstable here, their unenclosed running gear creating airflow patterns that induced oscillations in the frame. But the Mallard remained stable, its streamlined casing channeling air around rather than allowing turbulence to develop. Bray worked the firebox with systematic intensity, maintaining steam pressure at 250 pounds per square inch while monitoring water levels that fluctuated as the locomotive's motion affected boiler internals. The keelchap exhaust system was performing exactly as designed, creating powerful draft that kept the fire burning intensely while minimizing back pressure on the cylinders. At 120 miles per hour, the Mallard exceeded the speed where German engineers had calculated that steam technology reached its practical limits. The locomotive was still accelerating smoothly, its mechanical systems operating within stress ranges that remained below critical thresholds. The speedometer needle climbed past 125 miles per hour as the Mallard reached the steepest section of Stoke Bank. For approximately 300 yards, the recording instruments captured sustained speeds that no steam locomotive had ever achieved. The maximum recorded speed reached 126 miles per hour, a velocity that represented not just a new record, but definitive proof that steam technology retained capabilities that established engineering opinion had dismissed. Then Duddington felt the change, a subtle vibration through the controls that warned of approaching mechanical stress limits. The middle cylinder's big end bearing, subjected to forces beyond its design parameters, was beginning to overheat. He closed the regulator immediately, allowing the locomotive to coast as speed decreased. The bearing failure that followed was dramatic but not catastrophic. Metal temperatures exceeded lubrication tolerances, causing the bearing to seize partially before emergency cooling prevented complete destruction. The Mallard coasted to a controlled stop at Peterborough, its record established but its middle cylinder disabled. Inspector Jenkins examined the recording instruments with an expression that mixed professional satisfaction with amazement. The data was irrefutable. The Mallard had sustained speeds that physics calculations had said were impossible, and had done so while maintaining mechanical stability that demonstrated genuine engineering advancement rather than reckless experimentation.